Hello and welcome. This is an instructional video series in which we will show you how to convert unstructured network inventory data. Our customers often have their physical network inventory data stored in legacy systems. Network data that is stored in legacy systems is often not structured and therefore is not suitable for direct migration into a new operational support system. Customers want to minimize costs and reduce the time needed to convert and migrate unstructured network inventory data into their new operational support system. In Part 1, we will create a topologically correct trench network from CAD graphical elements. The network documentation that we will be converting is from one of our customers. It is a big utility company in Germany that had its entire network inventory data stored in more than 22,500 DGN files. In this video, we will show you how to structure legacy MicroStation DGN files with minimal costs and time effort. However, the same approach would work for converting any other type of legacy network inventory data stored, for example, in DWG, SHP, MS Visio, PDF files, etc. We successfully converted the customer's entire network documentation using a tool called Interactively Assisted Converter. We will show you how, step by step. First, we start the tool. We log in, and then we open one DGN file. As you can see, the DGN files are organized in groups. You can filter out or search for any DGN file. We will select and open only one. For example, this one, Dieselstraße 3. Now, what we have here is a map covering some small part of a city. If we zoom in, we can see property lines, buildings, and annotations. But there is also an electricity network with dimensions that is documented. In this case, all the data is already georeferenced. Now we will focus only on the network inventory data. To be exact, what we see here is not a true network. It only looks like a network. Let's see why. For example, let's take a closer look at this joint. In the legacy data, it is represented with two circles. Actually, it is two polylines. This is the first one, and this is the second. So, instead of one point, the network node is represented by two polylines. If we want to structure this network node, we need to convert these two polylines into a single network point. We can also see these orange lines. They represent trenches. If we select one, we can see that this line is not split where the nodes are. Most of the network lines in any legacy network data are just long lines without any splits. If we move a bit further down, we can see that this same line randomly splits into two here. Well, it should not, because there is no node there. So this is another flaw in the legacy data. Another very common problem in legacy data are polylines that are not snapped. If we zoom in, we can see that this polyline, which represents a trench, does not end in the center of this node. To summarize, what we have seen are just a few simple examples of what unstructured network inventory data looks like. There are many mistakes in the legacy data, and in order to successfully migrate this data, we first need to structure it. Now that we understand the problem of unstructured data, we will show you how to create a geometrically and topologically correct trench network with minimal effort. The interactively assisted converter structures the legacy data in multiple processing steps. In this case, there are 7 steps. Each step improves the data quality further. In the end, the data is fully structured and ready to be migrated into an operational support system. We start with Step 1. This step converts legacy polylines representing trenches. It only takes a second or two to convert the trenches in Step 1. Now, if we switch on the results of Step 1, we can see that the polylines are split, snapped, and merged where such was needed. However, we are not finished yet. In order to complete the trench network, we also need to convert circles into network nodes. This is what Step 2 does. If we run Step 2, it only takes a second or two for the data to be processed. If we switch on the results, we can see 2 things. Firstly, it creates trench nodes represented by points located at the start or end of each trench line. And secondly, Step 2 identifies annotations and assigns them to trench nodes. For example, if we select this trench node, we can see that the value of one of its attributes is 36. The value 36 was assigned to the trench network node from this annotation automatically. We have converted circles and long lines into a trench network with annotations. If we zoom out, we can see that after running Steps 1 and 2, our trench network has been structured fully automatically. Actually, to be precise, there are 4 situations wherein the trench network has not been converted 100% successfully. In order to see these situations, we first need to turn on a layer called Tickets. Now, let's take a look at this dialog. You can see that for each of those 4 situations, a ticket has been created automatically. Each ticket has a short problem description. Moreover, each ticket is represented by a rectangle that helps us locate where the problem is. We simply click on a ticket and we are transported to the location. Obviously, the tool needs some help to convert those situations. The idea is to create one assist for each ticket. Let's see how this works. Let's take a look at this situation. We can see that this trench node is marked with a ticket because it has not been assigned a house number. The annotation P19 should have been assigned to it. The reason why this did not happen is that the distance from the node to the annotation P19 is too large. It is beyond the tolerance limit. In this case, a member of the assistance team manually creates an assist. How is that done? Firstly, you switch on the layer called AUH. This is an abbreviation for Automation Help. All manually created assists are stored on this layer. Then we manually create a line that starts at the annotation P19 and ends on the trench network node. Then we select the assist named Connect a Text to a Point. This is like an instruction telling the algorithm what to do. Then we run Step 2 again. The result obtained is that the text P19 is now assigned to the trench node. If we inspect the attributes of the node, we can see that the value P19 is assigned. The remaining 3 tickets are similar in nature. We resolve them one by one, creating the same type of assist. We simply connect text to the point and then select the assist. Now we run step 2 again. As can be seen, there are no more tickets left, which means that the legacy data has been successfully converted into a trench network. The trench network is now topologically and geometrically correct. However, a trench network is not the only type of network documented in the legacy data. Some information about the cable network has also been documented in the legacy data. For example, polylines in violet color represent information about the cable network. These are cable extracts, and next to them are annotations that describe the type of cable. In the next video, we will see how the interactively assisted converter creates a complete cable network from such a limited amount of information automatically. Thank you for watching this video. Should you have any questions, please do not hesitate to contact us.